But can you give us kind of a big picture
Mhm.
explanation of loop quantum gravity?
Sure. So probably we have to start from a little bit before that. So a big picture of what we know in fundamental physics. So we know that the universe is made up of two parts basically. One part is matter or matter fields. The other part is space-time. So space-time is the arena where matter fields interact and move and all sorts of things. And many times when people talk about universe, they forget that the one important part of the universe is space-time. So they talk about universe ending, and by that they mean that some sort of things happen to matter fields that disappear or something happens, but the space-time is still there. So anyway, so there are
Mm-hmm.
two parts to the universe. The first part, which is the matter field or the matter fields, that part is explained by some theories. For example, electromagnetism describes the particles that have electric charge. And then we have two other theories, weak theory and a strong theory. They basically describe how atoms in more high energetic levels behave and interact.
Mm-hmm.
So this is about matter field. So previously there were classical theories, like electromagnetism was a classical theory, and people found out that you have to do something to these classical theories so that they match the observation. And that framework that they use is called the quantum theory. So they found that, for example, light comes not in a continuous system or way, but it's divided into small, what we call quantas, small packages or
Mm-hmm.
packets. So it worked well for matter field, and very good. We have the standard model of particle physics and everything. On the other hand, gravity or space-time, we we have everything is classical. So we know what is space, what is time, and people started to think about that. Okay, so what happens if we want to do the same quantization to the space and time? So maybe space itself comes in packets or atoms, and time itself. So they started to do that also to match these two theories of matter and the space-time together, because you cannot match two theories that one is classical, one is quantum. They cannot interact basically. So that part that what you want to quantize a space and time or a space-time is called quantum gravity, and the reason is that the field of gravity is actually a space-time. So you don't have gravity or a space-time. You have, you don't have gravity and a space-time. Gravity is a space-time. You can think of the universe as matter fields and the field of gravity, or matter fields and the space-time. So the gravity
Mm-hmm.
and space-time is the same thing. So when people talk about quantum gravity or quantization of gravity, they mean quantization of space and time. So this is the big picture of what we have. Then, so we can later go to what is loop quantum gravity as opposed to string theory or other theories.
Mm-hmm.
Um, but
I
if you
think,
want,
yeah,
we can discuss
yeah.
about this. Yeah.
Yeah, so before we actually get into the loop part of the quantum gravity, just wondering about the class. So I don't know if this is still a question asked, but at least like when I was still searching up like my limited knowledge, I think there was always that big discussion whether gravity is could be a particle, hypothesized as the graviton. So does quantum gravity support the fact that gravity is a particle, or does it? Because you explained that gravity and space time are basically synonymous, right? So if
Mm-hmm.
that is true, then how could gravity kind of be conducted via a particle? Maybe I'm misunderstanding this. Maybe you can clarify. But
No,
like,
no,
what's the situation there?
sure. So imagine, let's first start with a known field, which is electromagnetic field.
Okay.
So in electromagnetic field, you have a bunch of, so this is how field theory or quantum field theory works. In classical field theory, what you have is a bunch of particles, say electrons and protons, and then around them, they create a classical field. And by field, I mean something that is around an electron, for example. We don't know what that thing is. But whatever it is, it covers all the space around one electron. And if you put any other electron or proton in there, it feels a force on it. And
Mm-hmm.
that's the result of this field, that this is the invisible hand of the electron that reaches out to other electron and acts on it. Quantum field, so in this picture you had two objects. You had field and particle. One of them is like a wave. The field is like a wave in the sense that it is not non-local, if you want. It's always all around the electron. The other one is a particle, which is electron and is local. Now, quantum field theory changed this view a little bit. So it says that you only have fields. There are no particles in principle. These fields are fluctuating because of the quantum phenomena. We can talk about that later. But anyway, so they're just this going up and down, so these bumps and valleys in the field of the electric field, like the water in the pool. So sometimes they're small, going up and down in the water. And at some point, for some reason, some of those bumps become permanent. So there are excitations in the field. And then those excitations are particles. So particles are made up out of this continuous field. And then they affect the field, and field affects them. And how these two, suppose that you have two electrons, how do they communicate? Because it's a quantum theory, quantum field theory, you really can't have these continuous things like fields. So what happens is that around these electrons make the field also excited around them and create another types of particles if you want. And those types of particles are called photons. So those photons are force holders of the electric field. How do they work is that one electron is here, it kind of, well, this is very hand waving. I mean, it's not very, I don't want to go to technical things, but so this electron creates out of the field around it, creates a photon, for example, excitation. And this photon travels from electron 1 to electron 2 and affects its velocity or momentum. And then either repels the second electron, the first one via this photon, repels the second electron or attracts it if it's a proton. And that's how this is the picture of quantum field theory. So everything is basically a quantized field, and particles pop up and pop in and pop out of this thing. And that's why you also have the idea of creation and annihilation of particles, which you don't have in quantum theory. You have in quantum field theory, but you don't have it in quantum theory.
Oh, those are different things.
Yeah, there are two different things.
Okay.
So this is the picture of quantum field theory of matter fields. So this is what we know about the matter fields. In gravity, if you want to have this picture, again, you have to quantize this. And quantizing the field of gravity, as I mentioned, is basically quantizing a space-time, right? Because what you see as a force of gravity is nothing but the curvature of a space-time. So we've interpreted as force or field of gravity, but it's just a space-time, no bending. So you have to have this quantum field that makes quantum excitations and blah blah. So this force carrier that I talked about in the case of electric field with the photon, this in the case of gravitational field, if we had the quantum theory of gravity, would have been the graviton. So a mass creates a graviton around it, and then send this graviton to another mass, and then that affects the other mass and attracts it. Unfortunately, or maybe fortunately, I don't know, for us, it's good to not know some things in physics. This doesn't work. If you try to quantize the force of gravity like that, or field of gravity like that, you encounter lots of infinities, if you want, or unknown parameters that you can never get rid of. And technically it's called the renormalizability. So you cannot renormalize the field of gravity. It means that there are infinite number of parameters in there, infinities there. It doesn't work. It only works, this interpretation only works if your gravitational field is very weak. So you have a small curvature. For that, you can approximate something as graviton, as a particle, but at the heart of black holes, or the situations where curvature is very large, that description breaks down.